Hola, hi, this is Al, your statistics instructor. Let's get to work. So, the topic that we're going to be discussing here in this video is model selection. Model selection. So the question that we're going to try and answer is this. If we have two or more competing models, which one should we choose? So we will try and answer this question using hypothesis tests and information criteria. To illustrate these ideas, we will use a simple linear regression model. Okay, so let's refer to our lecture slides. Let's go to slide number 3. As you can see, we're going to be considering a simple linear regression model. Just as a reminder, we refer to this model as a simple linear regression model because it includes only one predictor. The error term, as usual in a linear regression model, has a normal distribution with mean 0, variance sigma squared, and the epsilons are IID, independent and identically distributed. As you may recall from your Statistics 302 course, a hypothesis test that we are particularly interested in involves the slope, beta 1. So we would like to see whether or not we have reason to believe that the slope is different from 0. Okay, so as we said on the slide, is there evidence that we have a linear trend, that there's a linear relationship between your predictor x and your response variable y? Okay. So, what we're going to be doing here is first, we're going to tackle this problem using tools from Statistics 302, things that you have seen back in that course. So we're going to answer this question first using a t-test, and then we will use a different approach, a likelihood ratio test. And if you remember, you saw that topic, you talked about that back in Statistics 260. Okay, so these are the two approaches that we're going to be taking here. And at some point, we are going to talk about the other criterion that I mentioned at the beginning of this video, information criteria. So t-tests and likelihood ratio tests are the first two ways of doing this that we're going to be discussing here. So in order to do this, let me produce some data. We're going to do a simulation to get some data, and then this is going to be helpful because we will know exactly what the value of beta 1, the slope parameter, is. So let me launch R, and we're going to copy paste these R commands. So as you can see with this set.seed command, what we're going to be doing is we're going to be producing a random sample, but by using this, the same seed, every time that you do this, you will get the same random sample. So you're going to be getting the same results. You know that if you exclude this command, you're going to be getting a different sample every time you do this. Okay, so the variance that we're going to be, well, the standard deviation that we're going to be considering is 4, and 1 represents the sample size, so we're going to be producing 50 random numbers from a normal with mean 0 and standard deviation 4. Then x1, it will be a sequence of numbers that starts at 1 and ends at 50. So the first element in that sequence is going to be 1, then 2, 3, so on, up to 50. Finally, we are going to be using this. This is going to be your predictor, your x, plus this random fluctuation that comes from this normal with mean 0 and standard deviation 4. So we're going to add these. As you can see in our simulation, beta 1 equals negative 0.5 and beta 0, the y-intercept, is going to be 3.1. Okay, so let me launch R. Let's copy paste these commands. There we are. So next, what we're going to be doing next is we will be fitting that simple linear regression model. That is, we're going to be estimating the parameters of that model. To do that, let me remind you that the R command that you will be using is LM. This is a special R command. LM stands for linear model, and the syntax of that function is this. First, you need the response variable, then you have this tilde here, and your predictor or predictors. In this case, it's a simple linear regression, so we only have one predictor. Then we're going to be assigning the result from fitting that model to an object that I am naming fit_1. Okay, let's copy paste this. Now, let's obtain that information that we need. We know that in this case we're particularly interested in carrying out a hypothesis test, right? Let me remind you that the hypothesis test that we're interested in is this one. Beta, the null hypothesis is beta 1 is equal to 0 against the alternative that beta 1 is different from 0. So first, let's carry out that t-test using R. So we know that to carry out that t-test using R, you have already fitted your linear model. So one thing that you could do to carry out that t-test is use the summary command, and then in this case, you have already fitted that model. We called it fit_1. Since we are particularly interested in the coefficients, you could add a $ coef or just use this. If you do this, you have more information here, but the only one that we care about is this one here. Okay? So let me show you. Using this summary brackets fit_1, you have all this information, residuals, and you have the residual standard error, so on. But we are particularly interested in this part. Let me show you what I meant by that idea of just using something additional. So since you want to pay attention to the coefficients, this is going to give you just the part that we're really interested in here, which is the t-test. Let me do this so we can see the results better. You know that here on the first column you'll have the estimates. So this is the estimate for the y-intercept, this is the estimate for the slope parameter, beta 1. This is the standard error from your test statistic. You know that if you divide that estimate by the standard error, that would yield the test statistic that is going to help you carry out that hypothesis test. H naught, the null hypothesis, beta 1 equals 0 against beta 1 is different from 0. We can see that this value is really big, an absolute value. And since we have 50 observations, the degrees of freedom for that t-distribution we know will be 48, n minus 2. So, and we know that as the degrees of freedom increase, a t-distribution looks more and more like a standard normal, which means that the probability of seeing something like this for a t-distribution with 48 degrees of freedom is nearly 0. As you can see, this is what we have. This is exact p-value. We have 21 zeros before that 3, so for practical purposes, that's 0. So if that p-value is less than alpha, our significance level, we know that we reject the null hypothesis. So this is practically 0, so we reject the null hypothesis that the slope parameter is equal to 0. Therefore, we have evidence that the beta 1 is different from 0. In this case, we already knew that. When we did the simulation, we knew the value, the true value of that beta 1 parameter, negative 0.5. Remember? Okay. So, using this approach, a t-test, that gives you overwhelming evidence that beta 1 is different from 0. Agreed? So let me show you a slide where we have that conclusion. Now we know where it comes from. Okay? So that's the first approach. That's the hypothesis test approach. So bear in mind that what you're doing here when you carry out that hypothesis is you are comparing two models. One that we could refer to as the reduced model, where you only have beta 0, the y-intercept, against a more complicated model that contains two parameters, beta 0, the y-intercept, and beta 1, the slope. Okay, let's talk about a second approach. Okay, first, note that your reduced model, beta 0, a model with just a constant, is a particular case of the more complicated model that includes beta 0 and beta 1. The complicated model includes beta 0 and beta 1, and see that the reduced model is a particular case of the complicated model. If you set beta 1 equal to 0 for the full model, then you end up with a reduced model. When you have this kind of situation, you have something that we call a nested model. So, the next approach that we're going to be discussing, a likelihood ratio test, doesn't have that restriction. You could be considering models that are not necessarily nested models, meaning that you could compare models where the reduced model is not necessarily a particular case of the full model. Okay? So, let me show you how we are going to be doing this for this example. Let me go to slide number 9. So as we said, the advantage of likelihood ratio tests over t-tests, for instance, is that the models that you're comparing, they don't have to be necessarily nested. Now, how you do that? How you carry out this comparison? So let's go to the next slide so you can see what the test statistic will be in this case. So the test statistic will be given by this, a chi-square distribution. We know that the chi-square distribution has a parameter that defines the chi-square distribution that you are referring to, the member of the chi-square distribution family that you're particularly interested in. So the degrees of freedom. So how do you determine the degrees of freedom for a chi-square when you're carrying out a likelihood ratio test? Well, the degrees of freedom will be given by the difference between PF minus PR, where PF represents the number of parameters for the full model, the more complicated model. And PR stands for the parameters, the number of parameters in the reduced model. The sum of squares for the error for the reduced model go here, and the sum of squares for the error for the full model go here. So this difference, n times the natural log of the sum of squares for the reduced model minus n times the natural log of the sum of squares for the full model, if n is big, this will have roughly a chi-square distribution with this number of degrees of freedom. Okay, so now what we're going to be doing next is finding the sum of squares for these two models that we are comparing. One model where you only have the y-intercept, the other one where you have the y-intercept and the slope. So first, let me remind you something from statistics 302. Let's talk about the reduced model. So sum of squares for the reduced model. So in this case, what I want you to remember is that the only parameter that you have for that reduced model is a constant. So the estimator for that will be just y bar. Okay, so let me write down what the sum of squares for the error of the reduced model will be. So what we're going to have here is this. You have your observations minus your predictions, and your predictions in this case are given by just y bar. So let me write that down here, and then you will be squaring these, and you do that for every single observation in your data set. Now this is what we refer to in linear regression as the sum of squares total. We know that one way of finding the sum of squares total would be this: n minus 1 times the sample variance, in this case the sample variance of your variable y. Okay, so in this case the sum of squares for the reduced model is equal to the sum of squares total, and the sum of squares total could be computed like this: n minus 1, where n represents the sample size, and sy squared represents the sample variance. Now let's talk about the sum of squares for the full model. Remember that the full model contains both parameters. By both parameters, what I mean is the y-intercept and the slope. So in this case, let me remind you that the sum of squares for the full model will be given by this quantity. Just like before, we're going to have your observations minus your predictions. So let me use that y hat notation for that quantity. I must have it here. Let me find it. Yeah, so here we are. Now let me remind you that y hat in this case is going to be, let me just add here the indices. This goes from 1 to n. That's for every single observation in our data set. And let me remind you that yi hat in this case is computed in a slightly more complicated way. It's not something as simple as just the sample mean. It's going to be beta hat 0 so it's going to be beta hat 0 plus beta hat 1, where these guys are your least squares estimators for the y-intercept and the slope, respectively. Okay, so another way of writing this down would be just, instead of having this, the difference between your observations and your predictions, you could use epsilon hat, where what we mean by that is the residuals. Agreed? Because that's the difference between observation and prediction, residuals. Okay? So, it turns out that we could easily find the residuals using R. Okay, so we're going to be finding these two quantities using R, and then we will use that formula from the approximation to the distribution of the likelihood ratio test. We know that asymptotically that difference, that function of the difference between these two quantities will have a chi-square distribution. And in this case, the number of degrees of freedom that we will need will be 1, because we have two parameters for the full model and one parameter for the reduced model. So let me go back to our lecture notes and compute the sum of squares for the reduced model, which for the reduced model that happens to be the same as the sum of squares total, which is just this quantity here, summation of yi minus y bar squared for every single observation in our data set. The other one, it's going to be just the sum of squares of your residuals. So let's do that. Let's copy paste this. let's find the sum of squares total, which will be the sum of squares for our reduced model. Let me clear the console here. Now let's find the sum of squares for the error. Right. So now we have those two quantities. Okay. Now let me go back to that expression where we have the distribution of our test statistic. Okay, so what we need to do is this. We need to compute n times the natural log of the sum of squares error for the reduced model minus n times the natural log of the sum of squares for the full model. Okay, so let's do that. So we know that the sum of squares total is this. So let me call that sum of squares of the error for the reduced model. Let me call SSE, that will be the sum of squares error for the full model. Okay, let me just double check that these two quantities are what we should have. Okay, sum of squares error for the full model. Great. So now let's just apply this formula. N times natural log of the sum of squares for the reduced minus n times natural log of the sum of squares for the full model. Okay, here we go. So remember that n is 50. Agreed? So here we go. So we have 50 times natural log of the sum of squares error for reduced model minus 50 times natural log of sum of squares error for the full model. So 98.49. Remember that we have 1 degree of freedom because the number of parameters in the full model is 2, beta 0 and beta 1, and the number of parameters for the reduced model is only 1 because we only have one parameter, the y-intercept. We know that the expected value for a chi-square is given by its degrees of freedom. So 98 is huge. So just for fun, let's find the p-value for this guy. So we would need to find the probability of seeing something as extreme or more extreme than that for a chi-square distribution with 1 degree of freedom. Let's do this. 1 minus p chi-sq, because remember that p chi-sq, it's a function that allows you to evaluate the cumulative distribution function, meaning the area to the left. Okay, so that's why we need to find a complement, 1 minus. So we want the area to the left, to the right of 98.49 roughly, with how many degrees of freedom? 1 degree of freedom. So for practical purposes, we knew that it was going to be 0, basically. So again, using this approach, likelihood ratio test, again, we have overwhelming evidence that the full model is better than the reduced model. But bear in mind, again, that the advantage of a likelihood ratio test over a t-test, for instance, is that in this case, these two models that we're considering, they don't have to be necessarily nested models. Okay? So, let me show you, to summarize what we said, our slide from our lecture notes. Okay, so bottom line, again, just to underline what we did, we have overwhelming evidence that the more complicated model, the full model, fits the data better. Okay, using this different approach, likelihood ratio test. Next, what I would like to do is talking about an approach where you compare models that take into account not only how well the how well the model fits the data set, but that takes into account something else, another feature of your model, that is the complexity of your model. Because based on here, the full model fits your data better, but it has more parameters in it than the simple model. So what we're going to try and do is using a criterion that includes in the selection process not only how well your model fits the data, how close are your predictions to the actual observations, but that it also takes into account how complicated your model is, the number of parameters. So let me show you two different measures that take into account that additional feature, the complexity of your models. So we have Akaiki's information criterion, for short, AIC, and Schwarz information criterion, and they refer to this guy also as BIC, as in Bayesian information criterion. Okay, as you can see, these criteria take into account how close your model is, how close the predictions from your model are to the actual data. So that's measured by the sum of squares for the error. But also, they are going to be penalizing the complexity of your model. So yeah, if you have a more complicated model, you're going to be able to fit your data set better. But now these two criteria also take that into account. So you will be penalized for being closer to your data if you require more parameters. That's what P represents here. P stands for the number of parameters in your model. So it's going to be penalizing the number of parameters that you use to fit your data better if you have a more complicated model. Make sense? So as you can see, the basic idea is the same. The difference between these two criteria are this: the quantity that you use to penalize the number of parameters in your model or models. So what we're going to be doing next is we will be applying these two criteria and see what the conclusion is, which model we should prefer after we have taken into account the complexity of such models. So here we go. Let's go back to R. So for Akaiki's information criterion, we know that the quantity that you want to compute is n times natural log of the sum of squares of the error plus the number of parameters, well, plus 2 times the number of parameters plus 1. Agreed? So let's do that for the reduced model. Reduced model. So we have 50 times natural log of the sum of squares for the reduced model plus 2 times, remember that p, in this case, p is 1 for the reduced model plus 1. So that's 424.71, roughly. Let's do the same for the full model. So in that case, it's going to be 50 times natural log of the sum of squares of the error for the full model plus 2 times, this time for this more complicated model we have 2 parameters, p equals 2 plus 1, so in that case we have 320.21 roughly. As you can see, again, using Akaiki's information criterion, we are going to prefer using this model because it is closer to the data, even we have taken into account the number of parameters in the more complicated model. Make sense? And we could do something similar for BIC. Let's do the same. In this case, remember that this part, the part where you penalize the number of parameters, is slightly different. So it's going to be n times natural log of the sum of squares of the error for your model plus the number of parameters times the natural log of your observations. So let's compute that for the reduced model. So it's going to be 50 times natural log of the sum of squares of your reduced model plus, in this case, remember that p, the number of parameters for the reduced model, is just 1 times the natural log of n, the number of observations. So 424.62 roughly. Let's do the same for your full model. So in that case, it's going to be 50 times natural log of sum of squares error for the full model times, in this case, p, the number of parameters, is 2 times natural log of n, your sample size, 50 in this case. So that's 330.04. So again, using both criteria AIC or BIC, again, the more complicated model is preferred, even after you have taken into account the complexity of the model. So it's closer, even after you have taken into account this, that it is more complicated, it is worthwhile to use the more complicated model. Okay? So let's summarize what we have here. As we said, both criteria are pointing into the direction or suggesting that it is a good idea to use the more complicated model instead of the simple model. Okay, let's summarize what we did here. So the question that we wanted to answer was this: if we have 2 or more competing models, which one should we choose? So the way that we tackled this problem was using first what you knew from Statistics 302. So we carried out a t-test. The disadvantage of that hypothesis test approach is that the models that you're considering there have to be nested. So what you could do instead to overcome that kind of obstacle is using a different approach, a likelihood ratio test. Using likelihood ratio tests, the models that you're comparing, they don't necessarily have to be nested models. But what they don't take into account necessarily is the number of parameters there in your model. Makes sense? And the thing is that if you have a more complicated model, then you are going to be able to fit your data more closely. But to take that into account, you could use another criterion or criteria. A Kaikis information criterion or Bayesian information criterion. Both of these two take into account not only how closely you fit the data, but also the number of parameters in your model to get that better fit. Okay? Well, that's it. See you next time. Take care. Bye.